Good morning, everyone. Thank you to be here for this fourth and last session of this course. Last session for now. Who knows? Maybe there'll be a follow-up one day. If I'm invited again, I will come with pleasure to discuss other topics in quantum foundations. So first advertisement. So it's written here on the board. 𝗰𝗵𝗽𝗁𝗿, so a researcher at LIS, is giving a doctoral course called quantum correlation at LIS, so in March. If you want to have more information and register, you can follow this link. Today, if you like what we do today, really today's course can be seen as a preparation, introduction to 𝗰𝗵𝗽𝗁𝗿 course. So if you like what the topic we discussed today, I can only strongly encourage you to go and see what Ravi has to teach you, because he's a great researcher and he's a world expert in quantum correlations. This course today required me a lot of work, much more than the previous sessions, not because it's intrinsically more difficult, but because maybe I spent a lot of time thinking on the measurement problem. Whereas, I mean, I know Bell theorem, of course, quite well. I've been, learning it for years and all these other results. But when I give a course, generally I want to, be extremely comfortable and know perfectly well what I'm explaining. And I try to do something very ambitious. So because I think most of the references, the textbook references on Bell theorem, are not, from my point of view, are not satisfactory. There are some simple questions that they don't answer. We'll go through that. And so I will try to explain why I'm not satisfied with most approaches from time to time. And so I try to do something better than what I know exists currently in the literature. So of course that in 1 week, preparing this is, you can imagine the challenge. And so, yeah, I'm not sure I will be entirely satisfied with what I'm presenting today, but feel free, as usual, to ask questions anytime you don't understand. And I do my best. I did my best, and I hope you will still understand something. The difficulty with Bell theorem is not in the math, just like the previous session, actually. The difficulty with Bell theorem, and it is objectively difficult because everyone struggles with these results. Everyone struggles to understand it, to interpret it. No one has the same, draw the same conclusion, etc. But the difficulty is not mathematical. You will see the proof, like it's just a few lines. The difficulty is conceptual. So to introduce Bell theorem, so of course the fourth section here is the longest and the main one, but to introduce it, we'll go step by step with simpler example, following the same methodology, each step trying to do a little bit better than the previous example. And to me, it's the best and maybe the only way to motivate Bell theorem and really understand why is Bell theorem so special compared to other simpler approaches we could have. So the general aim of the chapter, as I wrote here, is to see which kind of probabilistic theories could be used and be successful in physics. Given that we, in some well-chosen experiments, especially the quantum ones, we have observed some weird statistical behavior. So already remember the previous session, I emphasized a lot on the TPF, the total probability formula, which is violated in quantum experiment, which was not obvious at all. The first time we observed this experimentally was a landmark. And we will see today there are other statistical patterns, quite strange, that constrain the class of probabilistic theory that have a chance that to be successful. So, very important to understand. First of all, this chapter is not about quantum mechanics. Nothing to do with quantum mechanics. Almost nothing. We do something theory independent. So we look at the universe statistics. So this is just what is written on the experimentalists' notebooks everywhere around the world. And the conclusion we will draw will only be about the observed statistical patterns observed by humans in our world. But if tomorrow quantum mechanics is superseded by a new great fantastic theory, and no one is using quantum mechanics anymore, the conclusion will still be valid because it was just about empirical statistics, okay? So the point of view, the perspective is theory independent. Our conclusion would remain valid if quantum mechanics or any other theory is superseded by possibly a radically new theory. A new theory, okay? We only study the empirically observed statistics. Okay, so this is very important. This chapter is not about quantum mechanics. So from time, of course, why do we study this in a quantum mechanical course and not in any other course in physics? Because these weird statistical patterns occur in experiments involving quantum objects. But it doesn't mean it is independent of the formulation of the theory. Okay, so general methodology that we will follow. So this is the methodology of Bell theorem, but also all the other examples. So first formulate some metaphysical assumptions about the world. Metaphysical assumptions about the world. One or a couple or a list of them. Translate them mathematically. Into properties of the probabilities. This is the second point. Third, once you have this list of mathematical properties, well, you derive a signature like an inequality or something that any model satisfying these properties will have to satisfy. So derive a signature, but it has to be a testable. So an empirically testable. This is the big challenge. Empirically testable signature that any model satisfying these properties must display. Okay. Typically, Bell inequality is one of these examples. 4. So you know that if the universe satisfies these properties, these assumptions, then any theory will have to display this mathematical signature that is testable. But because it's testable, then you do the experiment. So perform a well-chosen experiment, and hopefully that violates this signature. And if you do this experiment and you see a violation of the signature, then you can conclude that at least one of the metaphysical assumptions must be rejected. So you know that we live in a universe in which at least one of these metaphysical assumptions is rejected. Okay. First, very basic example that I'm not sure it's anywhere in the literature, but it's so simple and it's already very conclusive, and so if you once you see it, you understand that all the more complicated examples have to do something more than this first basic example. So it will be based on what we studied last time on the measurement problem. Remember the metaphysical assumption translated into the TPF. So we're going to this. So suppose, so first, each time I introduce an example, I will also introduce a setup, meaning I don't specify what's the system, and remember it's quantum theory independent. So I just say, suppose we have one system and just two variables, but it can be anything, right? Satisfying this setup. So here, the setup, as I said, is just one system and two variables. Later, it will be more and more complicated. So we have a system. For which two variables a and b can be measured. So I will draw a little box, little diagram that might seem strange at first, but with more and more examples, you will get used to this. So this is just my system, and the arrows going up are just outcomes of measurements. And arrows coming in, what we see later, there will be parameters of my experiments. For now, no parameter. Now, what are the assumptions I will take? So assumptions. So first, the metaphysical assumption. Well, I propose let's start with, remember the assumption of last time, which I called epistemic ignorance. So in this course, the metaphysical assumption, I will always write it in capital letters so that we see each time, precisely when, I'm invoking a concept, metaphysical concept. So epistemic ignorance. This is the title of the concept, the assumption. And remember, I define so EI. I called it this way last time for short. And so first, the assumption can be expressed in words. So remember how I expressed it last time. Even though the actual value of a variable is not known, it's still definite value among the possible ones. Remember, I call it epistemic ignorance for short, but it has to be understood that like all ignorance is epistemic. And remember, we define the measurement problem as the violation of this and as the existence of ontic ignorance. But let's try to assume that and see where if we can find an experiment that lead us to reject this assumption. Okay. So second step, we have to translate this into math, into a property of the probabilities. So you already know what I will propose. So mathematical translation. What do I choose? I choose, of course, the TPF. But first, there is more than this, much more than the TPF. Remember, I said that last time I said that Kolmogorov axiom or Kolmogorov vision of probability is Kolmogorov axioms are the axiom of epistemic ignorance. Kolmogorov probabilities is the general model for a world in which EI is satisfied. So, in fact, the translation of this is huge. It's there exists a probability space omega, and I don't write the sigma algebra. We don't care in this course. And also there exist two random variables RV for short that we call A and B. Two variables from the probability space, let's say revalued, for example, that describe the system accurately, I should say. By which I mean that P matches P. What do I mean? This is the model, probabilistic model on the probability space. And what is little p? This is the observed relative frequencies. What is little p? Little p is what is written on the notebook of the experimentalist at the end of the experiment. That's very clear, very concrete. So p of anything is the table written on the experimentalist notebook at the end of the experiment. Very concrete. This is something I almost never found in the literature, but it's crucial to understand Bell's theorem, to divide into these two objects.
Do you mean the experimentalist has a lot of boxes and performs a lot of experiments and writes down statistics?
When we do a Bell experiment, for example, we prepare a very big quantity of system in the same initial state, and we do a lot of measurements with parameters changing, and each time you obtain a click, so you see, oh, I measure the polarization up or polarization down, and so I do a cross in my notebook, and then I have many crosses in my tables because I have, for each parameter, for each result, plus, minus, did I measure along this axis or this axis? I have many results, and then I compute the relative frequencies of the number of crosses, and so yeah, I get this P. Now, so this is the math translation. Now, testable signature. Well, if EI holds, so, well, this is the translation of EI. So if I have this, then the quantity which I call delta this should be, so yeah, it's just the deviation of the TPF. But this is expressed in terms of little p. So it's really something you can compute from the experimentalist notebook, apparently. And so the experimentalist can compute such a quantity in the end of the experiment. And this should vanish if P is accurately modeled by a probabilistic model P. And because it's a 𝗏𝗺𝗺𝗿𝘆 model, it should satisfy the TPF. So yeah, there is, of course, a problem in this. I'm lying here, but yeah, why am I lying?
I mean, in each experiment, can the experimentalist only choose to measure A or measure A and B? Or?
Yeah, exactly. That's why I'm lying. Thank you for the question. I'm coming to this. This is the crucial weakness of this argument. But I just want to do it. Pretend it's conclusive. Do it, and then in the end show why it's not exactly conclusive and why we need to do all the other more complicated setups. But so I pretend it works. So yes. This is expressed in terms of little p. So these are well, no, I will not write it because I pretend I'm lying, but I pretend I'm true, but I will not exaggerate this. So okay, apparently we could do that. This should vanish. Now experiment, because then I said, let's do an experiment and see, and let's see a violation of this signature. Experiment, perform a double slit or any interference experiment. So you can just measure a qubit in a complementary basis or anything, and observe that P measuring the electron at some point on the screen is not P of measuring the electron given it was on the left, P left, plus P electron And the same thing with right. So we do a double slit. We know that because p left is 1/2, p right is 1/2, and p of hitting the screen at x, given it was on the left, you know it's a pattern without fringes. Same here, and so but here there are fringes, so this is not equal. Good. Conclusion. Conclusion. EI has to be rejected. In my words, there exists ontic ignorance. And remember last time I argued that this is the very definition of the measurement problem. Okay, now, what is not satisfactory here? So it's not satisfactory, but it's already something. It's already a strong argument. We can already conclude something that, I mean, for any physicist of before the 20th century, would have been already and was already tremendous. So, and this is why quantum mechanics has puzzled everyone from the start. So, this is not nothing. This is already an important no-go. Yeah, I don't know. I mean, in quantum foundation, we use all the time this expression no-go results. I don't know if you're familiar with this expression. It just means you take assumptions together, which are in general untestable individually, or it depends, and you find an impossibility, and then you know that one has to be rejected. A little bit like, if you remember, Maudlin's presentation of the measurement problem was in terms of 3 assumptions, incompatible, and so this is called a no-go result. It helps you constraining what is possible or not. This is already an important no-go result. Physical variables cannot universally be modeled by 𝗂𝗺-Zeilinger random variables. This is already huge. Of course, today we are quite used of this, but this is already tremendous. Now, what is the limit? Limit of this approach. So it connects with your question. It replies to your question. P of x given left or right, and P of left or right. Well, they are well defined operationally. Each of them I can compute. I can do an experiment and obtain on my notebook some relative frequencies. So they are well defined operationally. And can be experimentally estimated. But not in one and the same experiment. There are 2 settings in the experiment. Setting 1, I just let the electron going through the slits, and I measure the position in the screen in the end. And setting 2, I measure the which way slit, and maybe I also measure the position in the screen. But there are 2 settings of the experiment, but not in the same setting of the experiment. So setting 1, setting 1 for P of x given left or right, you understand, and P of left, you must measure the which slit information, the which way information. Whereas the setting 2 for P of x, you must not measure it. And it's crucial, because if you do, then you don't obtain the fringes anymore. It's well known. So now let's be more accurate. More accurately, our setup was, or is, so remember the box. So you have outcome A, you have outcome B. Here would be the position, and here would be the left-right, for example. But in fact, you have a parameter, x, 1 or 2, which correspond to measure B or don't measure B. And from which, from this, a table, so the experimentalist table of relative frequencies. So how does the table look like? It's composed of all these. For all A and B and x equal 1, you get some relative frequencies, but also this. A, B, the possible outcomes of A and B. So this is a big table, right? The table written down on the experimentalist notebook at the end. And so yeah, is obtained.
You have a product of
No, yeah. We in quantum correlation we write this so often that we to ease the notation we don't write the. But that's a good question, because in some particular cases there will be a product indeed. By the way, you have this table, but you can, from this table, you can define other quantities which will still be denoted little p, because they are just obtained as, for example, marginals or post-selection on the notebook. For example, note that from this, you can define, for example, you can define P of B given setting 1. So it's not a primitive thing on your notebook, but it's just the marginal over A in the appropriate column of your notebook, right? So you just define it as sum over A. Okay, that's a quantity. Remark, crucial remark, because it's a definition, the TPF is by construction, by definition, defined at the level of little p. The question is, can a model satisfying the TPF at the level of big P accurately model what we obtain here if you add some other variables, typically a hidden variable or anything? We'll see that later. So remark, the TPF is by construction satisfied of little p. And if you want to know more, you can have a look at Laszlo-Chabot. I don't know how to pronounce it. A very nice guy in Budapest, from the guy from the quantum logic school. I was giving a talk in Budapest recently, and I met him, and he raised my attention on this fact. So you can have a look at it. His paper is called Critical Look at Probabilities in Quantum Theory or something. At the level of P. Yeah. Okay, good. But in those terms, in these terms, our signature writes or reads. So what the delta I introduced before. Now I can be more precise. Delta is in fact P of A in setting 2 minus sum of P yeah, what did I write here? Yeah, I can A given B something like this. And if this doesn't vanish, well, is it so shocking? In fact, it is a bit, but not as shocking as before. It is still a bit impressive, but not as much as the naive presentation I gave first. So now it's not as shocking as before, but still a little bit. As I said, and I don't change anything of this. It's still an interesting and quite huge no-go result. You cannot use Kolmogorovian random variables naively. Okay. Note. So I don't want to lose too much time on that, but there is another no-go result which I mean I found in this book. It's so by Asher Perez. So I mean it's very simple, but it's interesting. He notes that of course he doesn't present this in the same terms as mine, but he notes that you can already reach a similar conclusion by just studying a Stern-Gallac experiment. So for example, you know, similar conclusion by studying so I don't want to formalize it too much, but 𝗤𝗏𝗃 experiment along E1 or E2 or E3. What do I mean? This is your magnets, right? Suppose you define E1 this way, E2 this way, and E3 this way, so that it's 120 degrees between the axes, so that E1 plus E2 plus E3 equals 0. And then if you model, so you measure either along E1 or along E2 or along E3 the spin, right? Yeah, your electron comes here, and the magnet, you can align it here or here or here. 3 possible orientation of the magnet, so you measure spin along. No, it's 2D, and this axis is the axis of the incoming electron. And so if you if you try to model the system's variables by 𝗤𝗏𝗃𝗏 random variable. So maybe in the sequel I will write KRV because Kolmogorov is super long to write. Kolmogorov random variables. So you want 𝜇1, 𝜇2, 𝜇3 be defined on omega, and you experimentally you observe that they are plus or minus 1 valued up to h bar or something. It's impossible or it contradicts, or yeah, it contradicts the fact that if it's a random variable, you can do algebra with it, and so you should have the sum of the mu i's should sum to 0 because the free axis sum to 0. But this is not possible for plus or minus 1 valued random functions. Okay, impossible for plus minus 1 valued functions. Okay, I didn't want to dwell too long on this, but just another example. You don't need just a double slit or a 𝗤𝗏𝗃, and you already know that Kolmogorovian random variables cannot do the job. But okay, maybe I should have done this remark afterwards, because of the weakness that I showed here, the fact that you cannot do in one and the same experiment, and that in fact what you measure is this. And here we could do the same, because here you have 3 settings, so I can obtain relative frequencies given setting 1, setting 2, setting 3, and so in fact the contradiction would not be as shocking as before. So because of the limit explained above, we can just we can't conclude. Well, no, let's not write this. We need to do better. We need to do better. And stick very close to the actually observed phenomenon. So I actually observe frequencies P of something given some parameter. We must stick super close to this because here we were giving too much ontology. Just like here, we assume that 𝜇1, 𝜇2, 𝜇3 exist, even if they are not observed. And in fact, these are not things that you can compute from the notebooks of the experimentalist. Here, this is the theorist giving too much ontology. In particular, we need to do better because why do we need so? Because I mean, we could say, oh, we're already happy. We know that Kolmogorovian random variables are not sufficient. That's already nice. Yes, but Bohmian mechanics exists, and don't underestimate the historical role of Bohmian mechanics. It's the very reason why Bell started his research was because many people claimed to have proved some impossibility theorem for random variables, for hidden variable, especially Feynman. And so this extremely insufficient proof, and Feynman knew, he acknowledged that the proof was super basic. But still, everyone, as I said before, was so influenced by Feynman's book on foundations of quantum mechanics that everyone thought that, oh no, hidden variable, it's not possible because Feynman proved it. He knew himself that he wasn't proved. Because of that, most people did not even search for either interesting hidden variable theories or better impossibility proofs. But Bell was saying, so he's quite provocative against Feynman. He says things like, Feynman's proof is not only insufficient, it's just foolish. And why is it foolish? Because we have Bohmian mechanics. We know that there is a hidden variable that works very well, at least in the non-relativistic regime. So, big question I want to ask, and I don't have the answer, and I never thought about this question before preparing this course. In which sense is Bohmian mechanics not a Kolmogorovian theory? I don't exactly know how to ask precisely the question, and I have no idea of the answer. A few ideas, but it's really complicated. Before writing this question, so first, what I just said, in particular, and Bell was a Bohmian advocate. So the reason why he derived his theorem was not because he wanted to prove the non-existence of hidden variables. On the contrary, he wanted to constrain the possible class of hidden variable to show that we cannot really do better than Bohmian mechanics. Namely, there will be some non-locality in the gameplay at stake. But so, don't underestimate the historical role of Bohmian mechanics. If we hadn't such a nice, surprising reformulation of the math of quantum theory, giving the same prediction, if there was no such an appealing hidden variable theory, probably we wouldn't have, or possibly we wouldn't have the Bell theorem today, and all this course perhaps would not even exist, or not as developed as today. So in particular, we still know that a theory like Bohmian mechanics exists. So we want to constrain the class of possible probabilistic theory that can correctly predict the experimental data. And we know that it's possible to do something with, quite, which apparently maybe it's not in terms of random variables, but it's still, the idea is here, the feeling is here, and epistemic ignorance is not so easy to show that, to understand why Bohmian mechanics violates epistemic ignorance. So a big question. I don't have the answer, and I was led to this question while preparing this course. In which sense is Bohmian mechanics a non-Kozlov-Gorovyan theory? I have a little hints, a little clues of answers, but really, I think I'll be busy with this for a few years. So, second section, Leggett-Garg inequality. So let's do better. Leggett-Garg was first proposed. So, of course, the course is not chronological at all. In fact, Bell, in terms of chronology, would be the first, or maybe after these two. But I think for pedagogical reason, it's interesting to first show this one and see why, to understand what is so special again with Bell theorem. So first, proposed in Leggett and Garg 1985. First experimental test in 2010. Palacios and collaborators, paper in Nature, using superconducting qubits. Followed by many others. For review, you can see this one, ภิ and collaborators, 2014, for a review. So a review of the theory and the experiments. Oops. Many others, but so the others were not using superconducting qubits, but photons, defect centers in diamonds, nuclear magnetic resonance, phosphorus impurities, millimeter scale crystal, and many others. Good. Leggett-Garg is mainly used as a signature of quantumness or non-classicality in quasi or semi-classical systems. In system, I mean, it's mainly used in the quantum to classical transition, and you will understand why it's not so relevant in the purely quantum case. So, aim, we want to get rid of, so what failed in the double slit experiment? What failed is that there were two setups of the experiment. So you remember in my delta, the mic is working, yes. So what failed in the double slit experiment? There were two settings, either I measure or I don't measure. And this was creating a mess because the relative frequencies were not talking about the same situation. And also the role of the measurement disturbs everything. When I measure, it's well known, I destroy the fringes. And so we want to get rid of the parameter x and or it's still unclear to me exactly what's the logical knot here, but and or the influence of the measurements in which caused the which was the weakness of the double slit example. So new setup. Now there will be only one experiment, no parameter, but several measurements at different times. So setup. Measure a variable of a single system at 3 different times. T1, T2, T3. So the diagram here would be this. This is the timeline. Okay, T1, T2, T3, and my system exists here, exists here. It's the same system. I have no parameter, so no incoming arrows from below, but I have outcomes each time. So here, outcome A1, outcome A1, which is, let's say, plus or minus 1 valued. It's very convenient all the time. Here I have an outcome A2, plus or minus 1 valued, and here I have an outcome A3, plus or minus 1. What are the assumptions? So it's a mess, because in the original paper, well, no, I will write exactly what is written in the original paper, but then the mathematical translation, I disagree. From Leggett-Garg, so from the text copied from the original paper. First, macroscopic realism. How do they? So they write a macroscopic system with 2 or more macroscopically distinct states. Available will at all times be in one or the other of these 2 states. So this is, of course, very much like what I tried to capture with epistemic ignorance, of course. Macroscopically distinct states. So really, I copy the what is written in the paper, but well, you will see the limits in a moment. Second assumption. So of course, this captures some idea of objectivity. And by the way, they translate it in the original paper as a TPF, of course. I will not translate it as a TPF. You will see why. I struggled so much with this one. So non-invasive measurability. They write, it is possible, in principle, to determine the state of the system with arbitrary small perturbation, arbitrary small perturbation on its subsequent dynamics. Okay, this is so what they write. Now, what is the math translation? So now I will not follow what they do in the paper, because they, while preparing this course, I understood the maximal importance of little p, big P, the model, and in the paper they mix everything so that it's very unclear, and it's very unclear where they use this assumption exactly. Although it's clear it's needed intuitively, but mathematically it's super hard to disentangle everything. So I propose a mathematical translation of both of them. So for now I don't see really how to do better. So I would say, like before, there exists a probabilistic model, so a probabilistic space, omega and p, and 3 random variables, n1, a2, a3, plus or minus 1 valued, that correctly describes, so like before, correctly describes the system statistics that is p a1, a2, a3 must equal p a1, a2, a3. Super important remark, but this would deserve an entire course in itself. No, it's all the time consider it's not a product. If it is, I will say it, but for short, yeah, here, super dear remark, and this would lead us to the foundation of probability theory.
So these three,
yes,
there are 3 random variables because there are 3 different times.
Yeah, you measure a system at 3 different times, you get 3 outcomes, and so in your experimentalist notebooks, you get this. Relative frequencies.
The first assumption,
this one.
Is written 2 or more macroscopic.
Yeah, 2 or more macroscopically distinct.
At the end, you consider only 2 states. At the end of the phrase.
Ah, yes.
Or the order of these 2 states. In the first sentence.
Yeah. Okay, let's. It's not very important. Yeah. And here we do just plus minus 1. So let's do 2. But in fact, they write 2 or more, and maybe I didn't copy it exactly. Yeah, of one or the other of these states. Yeah, that they write here. sorry, it's me. I added a 2, but two or more. In fact, it's true, but we don't care. At least 2, we don't care. And here in the model, I propose ±1 because it's convenient. So let's, but it's not important. It wouldn't change anything. Yeah. So I said, look here. I replace this by this, and there could be an entire course about that. It would lead us to the foundation of probability theory. There are so many big questions. First, how come this exists in the first place? How come when you do an experiment, it always converge to something delfinite and very quickly? And second, when do you know that? When do you say that your model matches the relative frequencies? Because this is not defined at first, a priori. When are you satisfied with the model? And how many experiments can you afford to do? Because perhaps it's not you know, it's not precise enough, but perhaps if you do 1 billion more experiments, it will converge, or it will get. You will in fact, maybe you have an accurate model, but you just don't know it because you couldn't afford enough experiments, and yeah, many other big questions like that. In particular, so I add this just to emphasize because here it might be unclear where do we use the non-invasive measurement, and I agree, it's kind of unclear. I struggle so much with this. I don't have better for today, but in particular, at least we can say each AI has a predetermined value unaffected by the measurements. But I'm not very happy with this sentence. Maybe you will not be happy either. Yeah. Testable signature. So if a model satisfies this, can we find a quantity that can be computed only from this? That is impossible if there is a model matching it. So if MR plus NM holds, define the correlator. So it's interesting to go step by step with all these experiments, because we introduce slowly but carefully all the important objects for Bell theorem, so that when the Bell theorems come, you don't have everything coming into your head. So define the correlator EIJ okay, and this, mind that this is equal to 1 if AI equal AJ and -1 else. So the mean value, this mean value really measures how correlated the two variables are.
Is the product
here? yeah. These are really the random variables, whereas when I use the little letters, they are the outcomes. But I mean, it's not replying to the question, but just a side remark. We have so this product. So Leggett-Garg observed this, but I mean, it was not a revolution. It's very copied from Bell kind of observation. This is always true experimentally. So in every run, you obtain a little a1, a little a2, a little a3. You compute this. It is always true. Why? Because it's an identity. Indeed, if a1 equal a3, then you have a1 plus a3 times a2. Well, it's smaller than 2a2 because these one are just smaller than 1. Smaller than, because this is 1. And if a1 equal minus a3, because they are plus or minus 1 valued, so of course, then you have a1 plus a3 times a2. So this is 0. Okay, and because it's 0, it's smaller than, well, it is equal to 1 minus 1, which is smaller than 1 plus a1 a3. And exactly similar for the same for the other bound. Okay, so it's in every run, the experimentalists can check their notebook and found that in every run this is satisfied. So no testable signature that violates anything a priori. But when you take the expectation value, then it changes. Because now I take the expectation and I find that minus 3 this is Leggett-Garg inequality. And these ij can be computed from the table, the experimental table. You just, take some sum and mean values of relative frequencies. So these are experimentally accessible quantities. And now experiment. So first the naive one. Consider the precession of a spin 1/2. With, so Hamiltonian, you just take h bar omega sigma x Pauli matrix, and sigma z, the observable to measure at t0 plus delta t, t0 plus 2 delta t. And so quantum mechanics predicts k12 plus k23 minus k3 predicts something like that. Cos, you can compute the correlators by quantum mechanics, using quantum mechanics. And this is larger than 1 for omega delta t smaller than pi over 4. Conclusion, we have to reject either MR or NM. We must so again I'm lying. I'm sure you are not satisfied at all by this. So let's recap. We translated into math the two assumptions. We found that this inequality is true all the time for an experimentalist. But if you take the expectation value and you look at the correlation between the outcomes that you get in the three different times, then you get something that is experimentally testable from the experimental data, and which quantum mechanics predicts that in a well-chosen experiment, namely just a spin precessing, you should violate the bound. So we must reject MR or NM, at least one of two. But it's naive, because if you really do the experiment, you measure the spin, well, the quantum state collapses, and so you don't find these correlators, because you in fact you have invasive measurement. So of course, in fact you have to reject NM, but obviously you knew it from the start. So it was not useful to do all that. And also I wrote somewhere before, first experimental test in 2010 with a supercommunity qubit. So you understand that this is not the experiment that people did and thought it was a revolution. So yes, yeah. Yeah. Here, if they are all equal to -1, then we are in this case. So -1 plus -1 times -1 is still smaller than 2 times because A1 is not okay. Well, it's still true, isn't it? -1. It's still true. It's still okay. The proof is a bit longer, in fact, because -1 times plus -1 is -2 times -1 is 2, smaller than 1 plus 1. So it's true. Okay, there is a problem here. But I mean, we have better to do today. But you can check all the cases, and yeah. And so indeed, the proof is longer. Yeah. Check. A2 negative. Okay, but it's still true. Good. So, however, so no one did this experiment and conclude anything, because if you do it, you just conclude that you didn't have non-invasive measurement, but you knew it from the start. So to do an experiment which is meaningful, you need a system in which it's not obvious that you have non-invasive measurement, and more accurately, you need a system which is proved to be as invasive as non-invasive as possible. And if you show that, then you do the experiment, and then you conclude that, in fact, we have to reject the other one, macroscopic realism. So that's a test for the quantumness of the system. So, however, we know that non-invasive measurement is in general not satisfied. For quantum systems, everyone knows that. It's maybe one of the best known fact about quantum mechanics. So for quantum systems such as a spin particle. So more interesting tests involve system with what we call pointer states. So if one day there is a follow-up on this course, for sure the next session is about the theory of decoherence, and you will hear a lot about pointer states. But just to tell you today what it is: states that are robust to monitoring. This is why Leggett-Garg inequality is mainly used to test quantumness of a quasi-classical system. It's an interesting result for theorists and experimentalists in the field of the quantum to classical transition mainly. Now, back to our reasoning. So we wanted to do better than the double slit example. And we said, oh, in the double slit, the problem is that you have a parameter, you don't do the same experiment each time. And especially this parameter was, measure or don't measure the particle. And of course, when you measure, you don't have the same particle. So it's not a big surprise to have modified, to violate the TPF, the signature. So it's not a big deal. And we wanted to do better than this. And we said, okay, let's not put any parameter. And let's just have the one and the same system, all the time the same experiment, just you measure at different times. So you don't have any parameter. And to get rid of the possible action of the measurement, well, we cheated because we assumed it. we assumed that the problem was not existing anymore. We had the problem of invasive measurement, then we assume non-invasive measurement. Of course, okay, that's a bit cheating, right? So getting rid of parameter x and possible influence of the measurement led us, Leggett-Garg, in fact, they were not really motivated by the same, but I'm telling a little story. Led us to introduce NM. So this assumption is an attempt to save or justify maybe the 𝗦𝗵𝗽𝗺 random variable model. To justify it anyway, despite the problem we had in the first example. But it's cheating. And it's cheating, and I will write it. It is also a quite implausible assumption. So it doesn't cost much to reject it, right? So if the aim is to prove something super deep about the world, then yeah, we just proved that you cannot measure non-invasively, but we knew that from already a long time ago. So section 3, I skip it because I don't have time otherwise. Well, it was another interesting, little bit more complicated and slightly introducing slowly some tools for Bell's theorem, but we don't have time today, so we will have to be ready for a little bit more complex things immediately. So Bell's theorem. Seminal paper Bell 1964. Incredible history of this paper. So released in an obscure journal where really no one was knowing this journal, no one was publishing it in here, and also almost unnoticed for 20 years. Ten citations per year at most. And today, one of the most cited physics paper ever. At least quantum physics paper, this for sure, and possibly I checked, but it's super hard to know which one. If you know which one are the most cited paper, I checked, but it's very hard. Google doesn't provide any ranking. One of the most, well, at least quantum, that's for sure, but most cited. Quantum physics ever, and so it cannot be the first one because another one has at least 5,000 more citations, but it's the 𝗵𝗵𝗽𝗺 paper, so exactly the paper Bell was replying to. How many? How many citations? Just for 20,000 or yeah, and 25,000 for 𝗵𝗵𝗽𝗺 or something. Yeah, you're jealous, right? So argument refined by Bell in a series of papers. So notably the 71 paper, the 76, and the 1990 paper. Concerning the experimental tests, first, so this you know it, Friedman and Clauser in the 60s, 1972, but most notably, of course, by Dalibard-Roger in 1982, right? Nobel Prize 2022 for Clauser, Aspect, and also Zeilinger, who was the title of here, but we skip it. Sorry, Anton. Nobel Prize 2022 for these two. So yeah, most notably because Aspect closed the locality loophole. We'll come back to this, I hope. But you know the story. Yeah. So I will not write. It's a bit long, but orally, it's a fantastic result. I mean, Bell is my favorite physicist ever, probably, but at least for the 20th century. But it's a tremendous result with huge mathematical, physical, philosophical consequence. And there is even a political aspect, which I love to tell the story, so I just take 2 minutes for that. So we are in the Cold War context, right? In the 60s, 70s, and so hidden variable theories were in the East bloc, in the East side, were considered as much more suitable for the Marxists, materialists metaphysics, right? Marx is a philosophical. Marx built. Marx communism is embedded, has to be understood within a philosophical system in which materialism is very important, and hidden variable theory were considered to fit much better this Marxist materialism, and so. Annalisa told me, so I didn't check, but apparently even Stalin was, I didn't check, but apparently it can be found in Rovelli's book. Stalin decided that Bo'imel mechanics was the official interpretation of quantum mechanics in the East. But this is not about Bell theorem directly, but about Bell theorem in the late 60s, a few young Italian leftists, communists, were looking for new ways to organize society, and in particular scientific research. And they were, organizing alternative conferences and summer schools and so on. And they got interested in Bell's inequality in the 60s, 70s. So at the time where almost no one did. But interestingly, they were not interested because they hoped that we would violate Bell inequality and show that there is an incredible non-locality in the world. No. They were hoping that we would not violate the inequality, showing that quantum mechanics is in fact wrong in some regime, and showing that the idealistic bourgeois Copenhagish interpretation of the West with this strange wave particle duality and this unclear non-existence and both existence of things would be shown wrong thanks to Bell inequality, but not violated. So incredible story. Now, there are dozens of ways to present Bell theorem, the assumption, to decompose them into sub-assumption and to find all the logical links. So it was a terrible challenge. So if you want to know more, so there exist dozens of ways to present and decompose the assumptions. For more, for a very careful and thorough exposition, see, so these are among the most important, the main experts in today of Bell theorem, Weismann and Cavalcanti, 2017. So in Australia, there is a very important quantum foundations group centered around these two researchers, and so they are very active, but they are super specialized in everything that matters, that concerns Bell or local friendliness or quantum correlation, something like that, and Wigner's friend and stuff like that. Good. For a review, if you want to know more about Bell theorem, so a review of anything about Bell theorem, I can recommend something which is the Stanford Encyclopedia of Philosophy. It's online. See the Bell theorem entry in the Stanford Encyclopedia of Philosophy. Yes. You can check this if you want to know more. Another remark. The idea of Bell dates back to the 19th century. Because I think his name is George Boole, or one of the founders of logic. George or no? George? Mr. Boole published something. So he's well known for foundations of logic, but much less for his work in probability theories. So Bell's idea partially, and we will see what Bell did in addition, but partially dates back from Boole in 1854 who proved Bell's inequality, exactly Bell inequality, but for random variables. I will show a proof, not exactly what Boole did, but I mean the philosophy will be the same, and call it, or let's say Bell inequalities, call them conditions of possible experience. And he writes in the book, if you collect, not exact quote, but if you collect some correlations between events, or if you suppose that some correlation have been actually observed, if they satisfy my inequalities, Boole's inequalities, then they can come from actual experience. If they violate, they have no chance to come from an actual experience. But of course, experiment showed the opposite. But Popescu, 1994. If you want to know what Boole exactly did, very interesting paper. So let's see what Boole did. I mean, it's not exactly what Boole did, but expressed in modern terms, in my words, and the attitude is more or less the same. Expressed in modern terms, Boole proved a result of the following kind. So, theorem, or proposition. Let A1, A2, B1, B2 be some plus or minus 1 valued random variables with arbitrary law defined on arbitrary law. We have so expectation of A1, B1. This is a product, Serge. A1, B2. A2, B1. A2, B2. Smaller than 2. This is what we call today the CHSH inequality. But first, for now, this is Boole inequality, or he didn't prove that. But this is for random variables. I like to show the proof. Oh no, shit. We don't do the proof. Because the proof of Bell theorem will be exactly the same. It would have been very interesting to see the proof, but anyway. So if I give you some random variable, I give you only I don't give you the random variable, but I give you the correlations. You can check that some correlations are just impossible. If these correlations are tuned so that it violates 2, then you cannot find Kolmogorovian random variables that satisfies this. But the correlation we observe experimentally do violate this. So we want to derive a similar inequality without assuming any underlying Kolmogorovian random variable, because we know from the first example that it was precisely the weakness. it was the weakness of the previous examples. So we will show that any probabilistic model that yield the predictions, the little p, AB given xy, plus satisfying some locality property, even if A and B are not some random variables, must satisfy a testable inequality of this kind. Okay? To go beyond the random variable assumption or model, and include more general kind of theories, because not every theory is expressed in terms of random variable. Typically, Bowman mechanics clearly is not, because otherwise you could not have this. Let's introduce a single one random variable called lambda, living with value in some sets big lambda, on this proba space. This is the hidden variable. It's a very bad name. Bell did hate this name, because in Bowman mechanics the hidden variable is precisely the only thing you have access to, namely position. But anyway, and detail how lambda relates to the predictions for observed remember, this is the experimentalist notebook. And so the idea is that there is one random variable with some arbitrary distribution, and lambda contains some information about this prediction. But we don't do the following step of promoting A and B to actual random variable. Otherwise, it's trivial, and this is the problem of what I'm explaining currently now. I haven't found it anywhere in the literature, but perhaps it exists. But emphasizing on this step done by Bell theorem. What is so special with Bell theorem? You don't have random variable for A and B, and you have only one random variable here, and just you have a rule encoding a probabilistic rule allowing to compute prediction from lambda. This is the special step, and yeah, blah blah blah. So how lambda relates to the prediction of statistics? By some, and now it's big P. Okay, this is observed. This cannot be observed because you cannot observe the hidden variable, or you cannot know it perfectly. So this is only a model, and we build a model, big P, with a proba distribution on this object, plus we suppose that there are some probabilistic links between these parameters and the state of affairs, the ontic state of the universe, the hidden variable, allowing to compute A and B, but A and B are not hidden variable, are not random variable, while A and B are not random variables. Good setup. So the setup slightly more involved. Now you have a source here preparing some lambda, and but lambda has to be composed of two subsystems. You send one here, and here you choose a parameter y. So parameter 1, 2, or in fact you can have n parameters if you want, and Bob here gets an outcome b plus or minus 1 value. Then here Alice chooses a parameter 1 or 2 and gets an outcome a plus or minus 1. But importantly, the choice of the parameter and the experiment, this is the light cone, the past light cone. So of course the source is in the past light cone, but all this region, including the choice plus the measurement, is fully space-like separate state from all this region for Alice. And now assumptions. So the first is hidden variable. I give immediately the math translation. There exists a proba space omega p and a random variable lambda in taking value in the big step lambda plus some probabilistic link between lambda and the observable to measure, and so the link is of the kind as I wrote AB xy lambda. But this is big P. You don't have access to this because you don't have access to lambda, such that P, the model P, correctly predicts the observed relative frequencies. That is, so look, P, little p. So now you understand why we struggle for 2 hours to introduce that carefully. Now you know very well what is the little p, what is the big P, and I can tell you in the literature, if you find a reference where this is explained, please tell me, because I struggle like everyone for a very long time. And this is the core assumption of a hidden variable. And beautiful, this is a TPF. TPF when conditioning on the hidden variable, because you want to grasp an idea of objectivity. So you suppose this. Of course, normally in literature, everything is written in terms of little p, but there is a super deep conceptual difference between these two. Local causality, second assumption. So we have to add a new assumption because we want to do better than just the double slit. And we struggle for 2 hours just to do better than this stupid example, and to understand that the core thing to overcome is the random variable model. So local causality, this is crucial assumption of Bell. So here is the best way to explain it is in terms of light cones like this. And here is a region free. And so so a quote from Bell in 1976 to explain local causality. You will see how vague this is. He writes, the direct causes and effects are nearby, and even the indirect causes and effects are no further away than permitted by the speed of light. And then he translates this into math. But another way to say it is proba attached to region 1 are unaltered by specifying variables in region 2, provided when what happens, I think this is also a quote from Bell, what I'm almost exact quote. What happens in the past of 1 is already sufficiently specified. For example, by full specification of variables in region 3. And so a long sentence to say just this. B is independent. It's not a random variable, but it's independent of A and X. And A is independent of X and B. No, Y and B. Okay. This is local causality. So crucially, but thanks to preparing this course, I realized this, and I don't know how many people know that, but importantly, we do not need to assume, as Bell first did in the first paper. This is very important. In the first paper, he was not proving much, in fact. We do not need to assume something which we could call predetermination. Which would translate mathematically as P of AB given xy lambda is either 0 or 1. Meaning, if I specify the hidden variable, I specify everything. I specify the result of the experiment. Why is it so important? Because if you assume this, then A and B are just functions of lambda, so they are random variables, and so everything is trivial, and we don't do better than the double slit example. But Bell in 1964 he assumed this. So Bell 1964 doesn't do much more than just the stupid double slit experiment of the beginning. So let's just write this. So this is P. If P holds, lambda, A and B are just, or I would say outcome A and outcome B are just functions of lambda. So A and B exist as Kolmogorovian random variables. And so we don't do better. and we don't do and the double slit example. Well, a little bit better, okay, but not that much. And here, now, we merely need the existence of a law of physics or something, a law, a probabilistic law, P A B given xy lambda. This is your model, this is the law, but it's not the same as supposing a random variable. So you see the strategy of Bell theorem, and I realized that this thanks to preparing this course. What did Bell do, in fact, and himself, he didn't do it at first, but you don't want random variables, so your randomness, generally called omega in omega, is upgraded into a real random variable, lambda in lambda. And this way you can specify the links between the randomness and what you really observe, what really matters for you. And it allows you to build a wider class of probabilistic theory in which Boolean mechanics belong, to which Boolean mechanics belong. And if we didn't have Boolean mechanics, I mean, maybe it would have been much longer to come to such a formalization, you know, because it's easy to get convinced that, oh no, you cannot do better than random variables. Testable signature. So, yeah, okay, I will give the definition and not the proof, but this is Bell theorem, so I have to write it. Define a quantity that I will call A bar x lambda. It's the equivalent of a mean value, but I don't have a random variable, so I just define it. Out of these elements of my model, because my model gives me this kind of object, so by taking marginals, I have also this one. Okay, it's a real probability, P, big P. And the correlators. So that's why it was interesting to introduce Leggett-Garg inequality, because now we are used to having correlators. Correlators given a set of setting and a hidden variable. Well, this one is, again, it's just a mean value of the product of A and B, but they are not hidden variables, so I have to define it by hand. And now, the correlator, while integrating on the hidden variable. So now I take also the mean value on all the possible choice for the hidden variable. And crucially, this last quantity is experimentally accessible, contrary to the others. Because, look carefully. This is sum over AB, okay, but now this is, by definition of the hidden variable assumption, this has to match with the observed, and this is something from the physicist notebook. So the experimentalist at the end of the experiment can very well compute this. Belongs to the experimentalist notebook. Whereas all the rest are just hypothetical quantities. And now, last definition, denote S, X, X prime, Y, Y prime, lambda. It is the CHSH quantity, but for lambda first, with a given lambda. So X, Y prime, lambda. So if you remember Boole's quantity, Boole's theorem, it's not Boole at all, but it was the same, without the lambda, of course. And this is very famous, the Clauser-Horne-Zeilinger quantity. So CHSH quantity, S, X, X prime. And most references just introduce that almost immediately without so much details. So this is just these correlators. And just like Boole, we will find that this quantity has to be smaller than 1 under the hidden variable plus local causality assumption. It seems to say exactly the same as Boole, but no, because the proof is almost the same, but we have refined the model without assuming any random variable. So without assuming any kind of predetermination, and therefore we can say something about hidden variable theories like Bohmian mechanics. Again, where would we be today without Bohmian mechanics? I don't know. But so the Bell theorem. Here we are. If hidden variable plus local causality hold, S, X, X prime, Y, Y prime is smaller than 2. That's all. That's all. And then you perform an experiment, you find that you violate it, and that's all. And that's all. And therefore, we have to reject local causality, or, I mean, we know that any hidden variable model accurately reproducing quantum mechanical prediction cannot be locally causal. That's all. So experiment, well, I guess you know more or less. I don't have time to, if you invite me again, Tsirelson, I can explain all the rest. There is no time for this. Just in a few words. So yeah, experiment. Clauser or Aspe experiment. Find variables such that the correlations, so such that E so now the parameters will be angles cos 2 alpha minus beta. Now the parameters are just angles, and so choose alpha, beta, alpha prime, beta prime as this. So alpha, beta, beta prime, alpha, beta, alpha prime, where here you have pi over 8 Okay. Well, it yields alpha prime beta prime equals 2 square root of 2, strictly larger than 2. And in remark, so this was a whole section, but another time. 2 square root of 2 is the maximal violation of the 𝗬𝗃 inequality allowed or predicted by quantum mechanics, called, it's not so hard to show, called the Tsirelson bound. And it's a big mystery to try to explain or understand where does this bound come from, and can we find a principle that characterizes the set of the correlation we actually observe in our universe? Because clearly Bell's type correlation are just a subset of the observed correlation in the universe. And some people, so especially Popescu and Rohrlich, raised this question and tried to say, is, for example, no signaling, the principle of no signaling, the fact that Alice cannot communicate to Bob, whatever Alice does not affect the statistic of Bob and vice versa. If you impose this on the set of possible correlation, can you recover, all of quantum mechanical correlation? And the answer is no, not at all. They have found a table, an admissible table of correlation, little p, that maximally violates the CHS8 bound, so it's equal to 4, so really the maximal theoretical possible, and yet it's no signaling. So it's a big question today to try to characterize with a physical principle the set of observed correlation, and I think it's the latest development of quantum logic. I'm not entirely sure, but a lot of people have worked on this, and one principle which was quite popular at some point was called information causality or something, and many other proposals followed to try to characterize the set of observed correlation, but none of them was entirely successful as far as I know. And so it's still an open question, and you have a world expert in quantum correlation just next door, namely 𝗰𝗵𝗽𝗁, giving a course in March. So if you want to know more about quantum correlation and to know the crazy thing that people are now able to do much more refined than this, well, if you like this, just contact Ravi in March. Thank you for your attention.